Hello and welcome back to Calculus 3, section 12.9, Lagrange multipliers. This is the last section of the chapter. You already agreed that you won the test and won the quizzes and all of these other things for, I guess, April 2nd, you said? So we'll have plenty of time to review and work on this. So, Lagrange multipliers. We know how to find min and a max on the surface from previous section by the partial derivative, second derivative test and all that good stuff. Now what I'm going to do is I'm going to introduce a constraint. So again, think of the cookie cutter, right? But now that cookie cutter is not going to be straight lines, it could be curved line. And since I always teach in this classroom, right, Cal 3, this is actually me drawing this line on the object. So if you look at this bottle, you have a mathematical equation that governs the shape of the bottle that I'm holding. And then you also have mathematical equation which describes the black line I drew on it. So now, the section is teaching you how to find the minimum or a maximum on the surface of the object given the constraint, which is this black line in this case. So what I'm technically doing here is I'm trying to find the value of this point here, because that point is on the surface of the object and it's the minimum point on the black line. Now someone erased the top of this function on the other end, which was supposed to be, well, actually I can add that in. It's my bottle. There we go. So now we have a max on the other side. So, as I hold this bottle, you look at the bottle and you say, great, there is a mathematical function which describes this bottle. And the previous section will get us to calculate the maximum point of the bottle and the minimum point of the bottle. The new section is going to give you minimum and maximum points on the surface of the bottle along the black line which I drew. So that's going to be this point here and this point there. So that's how the two sections are different. Now, when I give you the word problem, it could be 12.8 or it could be 12.9. How do you know? Well, clearly 12.9, what we're going to do tonight, now, is going to have an extra equation, which is the constraint. You will be looking for the min and max along blah, blah, blah line, right? So we have extra constraint. And the Lagrange multiplier is a procedure. So we are going to introduce Lagrange multiplier lambda as a parameter, and we are just going to do the calculations from there. So it is a procedure. We learn the procedure for Lagrange multipliers, and then you just go and do it. So what do we need to remember here? we are going to compare gradients, which is the vector of partial derivatives, for those of you who don't remember. We are going to compare the gradients of the surface and of the constraint and multiply by Lagrange parameter on one side. So the procedure is to deal with del F equals the lambda del G. Whether you have a 2D system, 3D system, 10D system, it doesn't matter. This equation through the dimensions it holds. So that's the equation, and then g of x, y, z, whatever equals 0 gives you enough equations to solve the system. Calculus of this is a joke. Algebra of this, living nightmare. So let's dig into problems and do it. I want to go into, again, homework, because you guys can solve stuff. So example 1, we are going to do a problem, whatever. Let's do 6. So the surface, i.e. the bottle, the surface is given as xy squared. And the constraint, right, in the domain is a unit circle x squared plus y squared equals to 1. Now, I'm going to give you some words. This one over here is called the objective function, because that's where you're looking for min and max. And this one over here is called the constraint. Because you must be along this line. That's the black line I drew on the bottle. Now, objective function is your f of x, and the constraint function is g of x equals 0, so we have to move number 1 to the other side. So what do I have? I have function f of xy is equal to xy squared, and I have function g of xy, which is x squared plus y squared minus 1 equals 0. Now I need del f. Del f is a vector of partial derivatives. So fx is y squared, and fy, well, let me write, I don't know if you forgot. At the end, there was a spring break, right? No class for 2 weeks because of the snow. Probably I could be collecting like $1,000 each. Ask you, what's that, if you don't know, right? So fx is first partial derivative in respect to x. So for our function, that's y squared. And then the other one is 2xy, right? Partial derivative with respect to y. And now we need del g. 2x, well, gx, gy, which is 2x, comma 2y. Now, del f equals lambda del g. put this together, and this is where you will get those critical points. So I have a vector which says y squared 2xy is the same as lambda times the vector 2x 2y. And constraint function x squared plus y squared equal 1, or whatever way you want to write it. Guys, this is your system. I know it doesn't look like system yet, but the equality of gradients with the Lagrange parameter in and the constraint equation together create the system of equations which you can use. So now let's solve it. I have x coordinate equals x coordinate. So y squared is equal to 2 lambda x. And then I have a y coordinate is equal to y coordinate. So that's the second equation. 2xy equals 2 lambda y. And finally, x squared plus y squared equal to 1. 3 variables, 3 equations. Make sure you have that all the time. 3 equations, 3 variables, 4 variables, 4 equations, 5 variables, 5 equations, and so on. So again, the way we put the equations together is the first component of the first vector equals the first component of the second vector times Lagrange multiply, right? Because that lambda is a constant. It multiplies into both. You can distribute that first and then do the comparison. So you compare the first spots times lambda and the second spots times lambda. That's the order equation. If there's a third spot times lambda, and then this equation. And there we go. Calculus over. Time to do some algebra. We have to solve the system. This is called system of non-linear equations. And there are no rules. There's no set way that you say, oh, subtract 2 on both sides or divide by 3 on both sides. There are no rules here that are set in stone. It's just do it. That's all it is. Just do it. What happened? X equals lambda. See? Nice. Look at that. Do we all see this? Stare at it. I know. So now you know that some of you will never be detectives. Okay? This is some dreams and some hopes like gone forever, all right? If you can't see this. All right, so again, no rules, anything goes. The one thing you should not play with is cancel y's on both sides, because if you're canceling y's on both sides, that implies what? That you're dividing by y both sides, and that implies what? That y is not? Yeah, but it could be, right? So we don't want to divide both sides by y here. But we can make argument that x is equal to lambda because 2y and 2y is the same thing. Well, since that is equal and only x and lambda are different, right, then x must be lambda. Great. So that allows me to actually kill all lambdas and rewrite this system. So from the second equation I have this, which I'm going to plug in the first equation, since x equals, or lambda equals x, plug in 1 to get y squared is equal to 2x squared. Plug in 3. This is how it looks when it's too easy. So plug in 3. We have x squared plus, and now instead of y squared you have 2x squared equal 1. So 3x squared equal 1. X squared equal 1/3. And finally x equals plus minus square root of 3 over 3. Yay! Now I need my y's. This is where you also can be a little bit clever. Look at the equation. Y squared is equal to 2x squared. Well, you have what x squared is equal to, so don't use this one. You already have what x squared is equal, so plug that in. So y squared is equal to 2 times 1/3, which is 2/3. So that gives me that y is equal to 2 root 3 over 3, plus minus. Yay! What do I have? How many points? How many points do I have? 4. I have 4 points. Root 3 over 3. 2 root 3 over 3. Root 3 over 3. Negative 2 root 3 over 3. Negative root 3 over 3. 2 root 3 over 3. Negative root 3 over 3. And negative 2 root 3 over 3. Yay! 4 points. Are we done? No. Now we have to find the z values, right? To find which one is the highest and which one is the lowest. To find the min and the max. Because look at a bottle. You're looking at this, right, with your eyes, and there is the top point there. But if I don't tell you which of these 2 points is root 3 over 3 and negative root 3 over 3 and stuff like that, you have no clue which one is which, right? So now we have to plug these back into f, which is our objective function, to find the y values, and that will tell us the answers, right? So now I have f of root 3 over 3, 2 root 3 over 3. Actually, let me first write f of xy, so we don't forget the function, xy squared. So let's go. F of root 3 over 3, 2 root 3 over 3, is going to be root 3 over 3 times 2 root 3 over 3 squared. And that's going to be 3, 12, root 3 over 27. And now these cancel by 3. 4 root 3 over 9. Three to go. F of root 3 over 3 and negative 2 root 3 over 3. Well, when the negative goes there, we get the same value, because square kills it. Now we get different. Now we get a negative 4 root 3 over 9. And the last one is also negative. So, max, max, min, and min. I hope you're not disappointed. The procedure is extremely straightforward. You will find two gradients, equal them with a Lagrange parameter, get the equations, whether it's 2, 3, or 16, use the G equation as well to have enough equations, solve with whatever witchcraft you can master to get the X, Y, Z points. And then once you have all the X, Y, Z points, plug them back one by one in F and G, looking for the largest value for the max, lowest value for the min. And that's that. Now the horror is really within solving the system. You are always getting the nonlinear systems, you know, takes time. What was that? Okay, sure. 12. No, 14. So take this as far as you can. F of x is xy plus x plus y. And your constraint is x squared y squared equal to 4. Oh wait, the class ends at 8:20 or 8:50? 8:20. So that means okay. So you can try this one as homework, and then I will start next class by solving this problem. We still have to do the 3 variable 4 equation ones, so we still have lots of work to do with Lagrange. So we'll continue this. So there will be part 2 next on Wednesday in 2 days. Ciao.